So let's consider the case of the wave function, which is now interacting with a um, potential, a step function potential. But let's now think of it in terms of a probability current and how the probability current changes in this situation. So instead of writing out the wave packet form, the wave function is this Gaussian packet, which has a lot of complicated terms in it. Let's go back to the unnormalized states. And so we can write out for the incident, no, I'm sorry, for the total, we'll write out the total wave function in K0 as the incident A0 e to the I K0x plus the reflected b e to the minus I K0x times the step function plus c e to the I K0 squared minus 2m v0 over h bar squared to the 1/2 power x, again, times the step function. Now we're going to put it up front right there. So that's the total function. So now what we do is take this function and write out the currents. And so the probability current, the incident probability current, is ji h bar over 2mi times the psi star for the incident wave function, derivative of psi, minus psi times the derivative of psi star. Okay, so now we're going to put that in. So again, we're just going to consider the incident part. And so in that case, we would have h bar over 2mi a e to the I K0x, the derivative of a to the, this is psi star minus a, I should put a 0 in here too, e to the I K0x, so that's just the wave function psi, minus a0 e to the I K0x, the derivative of a0 e to the minus I K0x. And then the step functions, we're dealing with the incident wave function, the step function just becomes 1. Okay, so now we take the derivatives. So I can take the constant a0 out front. So I get an a0 squared. And then I have e to the minus I K0x, I K0, e to the positive I K0x, minus e to the I K0x, minus I K0, e to the minus I K0x. And so then those exponential terms multiply together and give you a 1. And so now what I'm left with is h bar 2mi a0 squared 2i k0. So that's lucky. So the i's cancel out and it's not an imaginary number anymore. And I get a0 squared k0 h bar over m, which is essentially the momentum divided by the mass. And so that is the incident current. So we could do the same thing for the reflected current and the transmitted current, where we just put those terms in, and to avoid doing all that math, I'll just give you the answer that the reflected current is B0 squared H bar, well, K0 H bar over M. Essentially the same number, but now modified by the normalization for the reflection. For the transmitted current, it is C0 squared H bar K0 squared minus 2M V0 over H bar squared square root divided by M. Okay, so now we have the three currents, these probability currents. And so if we want to get the reflection coefficient, we'd have to look and see what is the ratio of the reflection current to that of the incident. And so in that case, we get B0 over A0 quantity squared, which is what we had before. And so you notice this was a much easier procedure than what we arrived at before, when we had to try and normalize the wave functions and then calculate their probability by integrating over the probability density over all space. If we look at the transmission coefficient, that would be Jt over Ji. So the probability that's transmitted over the incident probability that comes in. And so now we write that out as C0 squared over A0 squared and H bar K0 squared minus 2mV0 over H bar squared square root over M divided by H bar K0 over M. So the M's cancel, H bar cancels, and what we're left with is C0 over A0 squared, the normalization constant, and K0 squared minus 2m V0 over H bar squared square root over K0. Now, if we were to, bring the K0 into the square root, then we would get C0 over A0 quantity squared out of K0 squared divided by K0 squared is 1 minus 2m V0 over H bar squared all over K0 squared. And that's 1/2. And so now we can actually rewrite these things as 1 minus V0 over K0 squared H bar squared over 2m. And if I remember, that's the energy. That's the total energy. So again, I get the same answer for the transmission coefficient in actually a much simpler form by considering what is the probability currents and then taking the ratios of those probability currents. And so that's, I get the same answer for them. And now we can calculate what is the, what's the probability of transmission, what's the probability of reflection. So a lot of times the current, while it may look a little more complicated, because you have to take the first derivative of the wave function and then multiply it by the complex conjugate, in a lot of cases it can simplify the problem if you attack it from there. If all you're looking for is things like these ratios of probability current. So there's another interesting case in quantum mechanics, and that is, well, what would happen if instead my incident wave function is now approaching from the side that has the potential. So what would happen if it comes in? And classically, what would happen is if you rolled a ball along a step, it's just going to fall down the step and then keep on rolling. But in quantum mechanics, what happens is once that wave packet crosses over, then I have both possibilities. So I would still have what we would call the transmission. Whoops. I would still have the transmission, like in classical mechanics, the ball would just fall down the step and keep on rolling. But in quantum mechanics, I also have the possibility that the wave function reflects. And so the particle, so it's interesting in quantum mechanics that I could have a particle at the high end of a potential come to the barrier of the potential and then bounce back, and then there's nothing physically bouncing back. It's not actually touching anything. It's just that there's a probability that there would be a reflection, and there's a probability that there would be a transmission. And so it doesn't matter what side of the barrier you're coming on, you would still get that because we have to consider all possibilities. Therefore, we have to calculate the probability that all possibilities are going to occur. And you have to basically conserve the probability. And so there's the chance that it would bounce back from it. And so so that's an interesting case, the fact that you can get a reflection off of something and not actually, physically bump into it. You're just getting the reflection because the potential exists. And so there is both possibilities of the particles going left and going right on the high side of that potential. Okay, so I'm going to stop here, and then we have one more case to consider in this step potential.